So today I'm going to deliver a lecture on nanotechnology concept as well as applications. So myself already the organizers have revealed about me. So I don't want to go my details because the time is very short. So I will go a little faster because the organizers have given only 1 hour to me. So but my slides and my presentations takes more than 1 hour. If I take more time, I'm sorry for that. Yeah. So coming to the contents of my talk, so my talk has been divided into four sections. The section one, I will give brief introduction about the nanotechnology. In the part two, I will explain the concept of nano. And third one is the applications of nano. So I will be focused mainly on these applications. Later, I will show you what work I have done during my PhD. So that is the fourth section of my talk on today. Let's go into my talk. So first I'm going to introduction. So in the introduction, I will give you the brief idea about the nanotechnology. I guess you people are very well aware about the nanotechnology. Just you can imagine here. So these are the course outcomes. You can think like that because most of the audience are faculty. So if you learn the nanotechnology, you can control the matter at atomic level. Sir, my cursor is visible to you? My cursor is okay for you, means the pointer.
Yes, sir.
Okay, done. Thank you. Yeah. So the nanotechnology is control of matter at atomic level. Everyone knows the materials are made up of atoms. So if you designed or manipulate your matter, it means that your material in the atomic level, in the means atom level, if you manipulate your material, so that is called nanotechnology also. So if you learn the nanotechnology, you can get the ability to build a materials using atoms as a building blocks. A little ambiguity in this sentence, I will explain to you. Here in this slide, you can see one photograph. The two children are playing with some toys. So those are building some type of architectures using these blocks. So from this image, similarly, you can play with the atoms. Just these toys, just imagine these are the atoms. If you arrange such type of straight line structures or 3D structures or hierarchical structures, so these all structures you can say materials. So similarly, so these two persons are the persons who learn the nanotechnology. So these toys, these small objects are called atoms. This straight line is the material. So if you learn the nanotechnology, you can play with these atoms like this way. Then you can prepare a desirable materials which can be useful for electronics or biomedical engineering or environmental whatnot. So you can prepare the materials which can be suitable for all the sectors, which is useful for mankind. So such type of materials you can prepare using this nanotechnology. Learn this nanotechnology if you engage or if you do the research. So the third one is manufacture of novel materials with novel properties. So if you learn the nanotechnology or if you studied the nanotechnology, so you have a ability to prepare the novel materials. Novel means the materials which can useful to us. So that materials you can prepare using this nanotechnology. So I can say these are the outcomes if you learn the nanotechnology. So everyone knows the nano materials. So everyone knows the nanometer is the 1 billion part of the meter. 1 million means everyone knows 1 billion is equals to the 100 crores. So 100 crore part in the meter, that part is called nanometer. So that is called 10 to the power of 9 meters. So it is a very, very small, we can't see by our naked eye. So it can be seen in transmission electron microscope. Those things we can see that type of nanostructures. And also someone confused, sir, what is the exact size for the nanostructure? So if the material in the nano, so how much dimension it should have? So we generally we called, I mean, theoretically we can call 100 nanometer size. It means that less than 100 nanometer size materials are called nanomaterials. So using these materials, if you prepare any missions or any applications, that technology is called nanotechnology. So the simple funda is, so the materials which have less than 100 nanometer size, those materials are called as nanomaterials. So this is about, say, a small introduction of nano. So definition of nano. So I already revealed these points in the previous slide. I mean, just now completed that slide. Nanotechnology refers to the branch of technology, everyone knows. So that deals with the manipulation of matter. I mean, we can play the matter, we can change the matter, we can prepare as per our wish. We can change that matter at atomic level or molecular level or supramolecular level. In these scales, if you manipulate the matter, that technology is called nanotechnology. Everyone knows atoms. So the materials are made up of atoms, a group of atoms arranged in a sequentially, I mean in the crystal form. So those are called molecules. If the group of molecules with some interactions, those are called super molecules. So in these scales, if we manipulate the materials, that is called nanotechnology. So the result of this nanotechnology is building a small materials, small missions resulting into fast powerful. It means that we can prepare a small missions or small materials. It has high powerful or faster performance. It means that I can say, so everyone say that the nano car. So everyone nowadays, majority of the people doesn't know the meaning of the nano. So the meaning of nano is not nano car. Why the name was given nano car for that is, actually when you bulk material come into the small, that is, that concept involved is nano. So the mainly nano is miniaturization, small thing, the bulk form converted into small form. So that result, that miniaturization was happened due to the nanotechnology. So that is the crucial role of the nanotechnology. Generally in the nano car case, the size of the car is very small compared to the conventional cars. That's why they use that term nano. But there is no crucial nanotechnology involved in that nano car as launched by the Tata. So, okay, now I will tell you the nanotechnology importance so far. So far, the science and the technology have been vastly developed in our current society. So on that, the nanotechnology products here, I have mentioned 1, 2, 3, 4, 5 examples I have given here. So if you understand these 5 examples, then you can think about how nanotechnology is important and how this nanotechnology is going to revolutionize the world, how it is governing the world and how it is governing the technology. So you will understand, okay, my perspective, I am taken these 5 examples to reveal the incredible importance of the nanotechnology. So the first one I have shown here, 3D molecular printers. So everyone knows the printer. In the printer, what will happen? So you will inject the ink. So that ink will be distributed as per our designs on the paper. Means it will be patterned on our paper. So that is the normal thing. But here, using this nanotechnology, the molecules can be printed. Molecules, for example, everyone knows the DNA. DNA very small materials. It is in around micro micro scale, 10 to the power of minus 6 scale, the DNA molecules are available, and proteins also. So these proteins are DNA, deoxynucleic acids. So we can pattern or we can print at our desired locations. Like this here, you can see in this example, this technology was developed by Parabon Nano Labs. So this 3D molecular printer. So the outcome of this printer is designing a novel drugs for the cancer. So in this technique, so each layer, so here you can see this yellow part. This yellow part is come from the layer by layer molecules deposition at this grid, 4 into 4 grid. So here our desired molecules are patterned at desired locations. So this will use in diagnostic laboratories as well as, because you people are electronics, but someone who are doing the electronics with bio, so those people can understand very easily about this concept. So similarly here 8.8 grid. So nowadays the very advanced drugs are developing using this technique, especially for cancer treatment. This is the main innovation or breakthrough technology came from the nanotechnology. This breakthrough technology came from the nanotechnology, because nowadays in future the drug designing is happening by this molecular printer. Next example is a stretchable gold. So this concept is completely related to your electronics. So stretchable gold means you can gold can, you have a ability to stretch, like if you see our cloth or if you touch our cloth, you can wrinkle that cloth, you can easily. Similarly, so this stretchable gold also we can wrinkle means so if many people are Telugu audience, so mudatalu, so mudataluga kuda cheyochu. It means that we can fold that sheets. So that type of stretchable gold have been fabricated using this nanotechnology. So what happened? What is the result of this one? So if this stretchable gold is commercialized, then immediately this one used for developing your motherboards, Cosmos semiconductor devices can be developed using this stretchable gold. So what happens? So in future, your motherboards also become a foldable, stretchable. Then you can implement these stretchable bolts on your cloths also. So you can wear these motherboards on your body in future because of this invention, stretchable gold invention. So in future, this all is going to happen because of nanotechnology. Next, coming to the third example, artificial muscle formation. So here the carbon nanotubes, everyone heard about the carbon nanotubes. These carbon nanotubes are the graphene materials, I mean carbon materials. So these carbon nanotubes are using to prepare the artificial muscle. Here you can see these two lines means these are the actually these are the some carbon nanotube threads. So it is a spherically folded coiled mutually coiled these two carbon nanotubes. Here you can see, so the beautiful of this work is, so when you this material, this carbon nano material keep in the water, so that in that water if there is a ions, this carbon nanotubes absorb that ions, then it will be coiled. So after coiled, if you give heat treatment for this carbon nanotube, it will be stretchable. Stretchable means it will become uncoiled. It means it become a straight. So this stretchable coiling, this mechanism will happen in our muscle. So that's why this is called artificial muscle. So in future, these things can be incorporated in our robots and those things. So this work was done by the University of Wollongong. So here that university has started this type of muscles fabrication. Next, coming to the interesting thing is electricity generating virus. So everyone told that virus is corona, so it infecting our body. But the advantages of the viruses, so that is M13 bacteriophages. The virus name is M13 bacteriophages. This was developed by the US Department of Energy Lawrence Berkeley National Laboratory. So these viruses can generate the electricity. So if you these virus paint on your floor, so then you will supply the electricity. What will happen? So this will also generate the electricity. The floor become very flexible. So the dancers will move randomly and very flexible. So such type of applications we can use these viruses, electricity generating viruses in clubs, and also we can paint these viruses on our shoes also. Then if you charge that shoes, so what will happen? You will get some generating field from that shoes because of this electricity. Then your movement, I mean your locomotion, will be faster. So such type of applications we may get in future by invention of these concepts using nanotechnology. The next one is stain repellent fabric coating. I mean, if you coat for example, here you can see nanoscale silicate pellets, polyethylene segmented polymer. I mean, silver coated nanoparticle, nanoscale materials on your cloths. The cloth become a hydrophobic nature. The cloth will get hydrophobic. It means that it will hate the water molecules. Means that fabric will hate the water molecules. What will happen? So the result is stains. There is no stains on your cloths. So if you wear this such type of cloths, so you will not see any stains on your cloths. So in future, the stain free cloths will become using this technology. This means here nanotechnology. So using this nanotechnology in future, you will see these type of inventions and revolutionary changes in our daily life because of these inventions. So from my point of view, I have shown these 5 examples because the time is short. That's why I'm going little fast and I'm not focusing on many more examples of these things. Next, I will go for one. So now the introduction part is completed. Now coming to the second part of my presentation, that is concept of nano. So I will reveal only one concept, that is the main concept, that is the fundamental concept involved in the nano. So here you can see this is very important because many people are nano doing this one, nano gives this one, nano gives this one. So, but how? So here I am telling that secret. Secret means everyone knows, the persons who are doing the nano. So the mantra of nano is high surface to volume ratio. I will reveal the meaning of this one later after understanding this slide. So first focus on this slide. So here you can see one cube with 1 meter of each face diameter. So in cube 6 phases are there, 1, 2, 3, 4, 5, bottom 6. So these 6 faces, each face is, the dimension is 1 meter. So if you take that 1 meter cube, so now we will calculate, I will just follow my scenario. So we will calculate the area. So 6 phases into each phase is 1 meter. So the total area is 6 meters. Now come to the next figure in this one. So here what happened, this cube is cut into how many parts? 1, 2, 3, 4, 5, 6, 7. One more is backside, 8 parts. So this 1 meter cube is cut into 8 cubes. So the area of these cubes has been increased 6 to 12 meter, doubled, because the surface is increased, because the okay, just a minute, I will show my video, then I will explain to you. Yeah, if you take the paper, yeah, you can take this paper. Just a minute, I will show you my video. Please see my video. Okay, so you can take this paper. So if you cut into 2 pieces, the size is decreased. Okay, what will happen? The surface of this one is increased, exposed to environment. So when the pieces are increasing, like see some more pieces is here, the surface area of this one is exposed more. So if you cut into the big paper is cut into small pieces, what will happen? The surface area is increasing. So similar concept was happen here. Okay, I will stop my video. Okay, now you can focus on my slide. So here So when you come here, so here 8 cubes, these 80 cubes have cut into small pieces. The area is cutting, the area has been increased doubled. So coming to the here, many, see, total 27 cubes. The area is 18 meters square. Then this cube cut into 0.1 meter cubes. The total around 10 to the power of 12 cubes. It becomes 10 to the power of 12 cubes. If you cut into this 1 meter cube into 0.1 meter size, so the area become 14.8 acres. Means the surface, the exposed area to this environment is increasing because this additional area is exposing to the environment, I mean exposed to the air. So that surface is coming into the active surface. Similarly, so here 1 mm is, it is the millimeter. Then what about the nano? So coming to here I have shown the nanometer dimensions. So here you can see, once you cut this 1 meter cube into 1 nanometer cubes, the total area of that cube occupies around 14 lakh acres. The volume is same 1 meter, but the surface is increased many times. So that's why the volume is constant, but the surface area is increasing. That is the beauty of nano. So that is the decreasing of size effect. So I hope you understand what is the high surface to volume ratio. Volume is same 1 meter. Then you cut into small pieces. The surface area has been drastically increased. See here, 6 meter square become 14 lakh acres. So it is huge surface area come into contact with the air. Air means the active surface become active surface because of this hidden part become into the active area. So this is the beautification of this nano. So what is the result? This increasing of surface area. Very simple. So this surface area is increased. So what will happen? See here. The atoms. So whatever the atoms here, so it will be hidden. In this case, this cube is made up of millions of atoms. Majority of the atoms in this cube are inside this cube. Those are not coming to the active area. Once you cut into 1 nanometer cube, all the atoms inside of this cube become active. So when it is in a bulk case, so very few atoms are exposed. When you cut into small pieces, so many of the atoms come into the active area. So that atoms will participate in your reactions or in your applications. It will be participate. Previously, if you consider only one cube, it will not affect all the atoms. But in nanometer cube, all atoms will come into the reaction part or whatever property you want to do. So that property will be influenced by all the atoms. But in 1 meter cube, only few atoms will participate. But into the nanometer size, almost all the atoms, generally the atom size is angstroms. So if you come to the angstroms, 100% atoms are coming to the active. See here, one graph is here. So when the dimension, I mean diameter of the particles are decreasing, the surface atoms exposure is increased. So up to 1 nanometer, so around this much, 80% of atoms will come active. If you go more down, Armstrong means 10 to the power of minus 10. So coming to the Armstrong, all the atoms in your materials come into the active surface. I mean active, because those all atoms are exposed to your desired applications. So that is the beautiness of the nano. So nano is stopped to here. 80% of your atoms are coming to the active. If you in the bulk state means it is in meter size like that, 10 to the power of minus means it is nearly micro case. Also the surface atoms not that much percentage active. But when you come to the nano 80%, but if you go into the Armstrongs, so almost all the atoms become active, but practically it is not feasible to generate the Armstrong materials, because if you consider the single atom case, those are in the radical state. Radical means those are having high energy states. Everyone knows that if any system in the nature, if it has a high energy, it will be not existed. So that's why we will call it as a radicals or intermediate state, not it's a stabilized state. So far in nature, the up to nanoscale, the materials can be stable, but up to Armstrong case not be stable. That's why this state we may not get. Majority of the materials we can go up to the nano size. So here you can see in the nano side, approximately 80% of atoms can be active. It will be come into the your participative role. So if this 80% of the atoms come into the active role, the properties of the materials will be changed. Let's see here one example I have shown. So if you take the macro scale of the sugar, so if you dissolve in water, obviously it will be dissolved. Macro scale sugar, if you take in bulk size of powder, means bulk size particles around millimeter sized particles or 1 cubes or millimeter cubes, it will be dissolved in water, because few atoms are interact with the water, so it has a feasibility to dissolve. But if you come to the nanoscale powder of sugar, so it will not dissolve in water. Nano sugar may not be dissolved at all, means the solubility property has been changed here, because majority of the 80% of the atoms will come contact with the water, so it will become a unstable to dissolve. It will become a inert because of more atoms are interact with water, so it will not try to dissociate into ions. So this was happen. So when you come into the nano size, the property of the materials can be changed. That properties may not be useful for mankind, may be useful for the mankind. We don't know. After the experiment, we can reveal that one. So here my point is, when you come into the nano, the property materials will be changed compared to the bulk materials. This is the conclusion statement. It means that we can say high surface to volume ratio. Volume is same, constant, but surface area is increased. So this is the concept involved in the nano. So that's why everyone is moving towards the nano, because of we will see wonderful properties. We will work on the nanoscale level. I hope you understand the concept of nano. So now coming to the, just I am giving one extra slide in this concept. So that is nanotechnology dimensions. Based on the materials, there is a classifications based on the dimensional space and the different nature of the material, I mean crystalline, non-crystalline. But here I have shown only the dimensional based materials, because this terminology you can see anywhere in the sectors, I mean electronics or chemistry or physics or biotechnology, nanotechnology or materials, mechanical engineering, metal matrices, everyone called in this terminology only. So here you can see, so based on this dimensional space, the particles or nanomaterials can be divided into 4 types: 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional. 1-dimensional means there is no dimension for that materials, especially the cubes, spherical shaped particles. These particles in the nanoscale, those materials are called 0-dimensional nanomaterials. So all nanoparticles, especially the shape is cube or the spherical, those are called 0-dimensional nanoparticles. Then coming to the 1-dimensional materials, that is carbon nanotubes, nanorods, these all comes under the 1D materials. Next, 2D materials. So 2D materials case, you can see the graphene sheets or tungsten sulfide sheets. So these are the examples of the 2D sheets. So these are comes under the two-dimensional because those have X and Y axis. This is the graphene sheet prepared during my PhD. These are the graphene sheets prepared at my stay at the University of Hyderabad. So next, coming to the third one is 3D, three-dimensional nanomaterials. So here you can see the nano flowers. These flowers are fabricated in our institution, in my current institution, SRK Engineering College. This work published in the High Impact Factor Journal. So here you can see the three axes, X, Y, Z axes. So that's why these are called 3D nanomaterials. So this is about the brief concept of nano. Next, coming to the applications. So this is a third section of my talk. So in this case, I will go little fast on this part because I have only half an hour. So during this time, so I have to show my research work also, because that is also one of the application of my work, application of nanotechnology. I will show you those things also. That work is very interesting. So after this part, I'm going to show that results. So that is good. That would be very interesting for you. Okay, coming to the nanotechnology. So here you can see some of the sectors: textile sector, I mean textile industries, biomedical, healthcare, food and agriculture, industrial. Okay, industry, these all are industrial. Okay, just ignore this industrial part. Electronics, environment, renewable energy. So what not? These all sectors you can use nanoparticles. I mean nanotechnology, you can use it. So in these all fields, you can use nanotechnology. That's why this nanotechnology is a multidisciplinary area. So in all the fields, this nanotechnology have some command. I mean, some involvement is there. That's why nano is always called multidisciplinary subject. So, okay, I will give you some of the examples of these applications. First, go to the textile. So coming to the textile, so using this nanotechnology, we will prepare the water repellent, I mean stain-free cloths. We can prepare using nanotechnology, and anti-static properties. I means that anti-firing. So it will give firing. Fire means it is a resistance to the fire. That class also we can prepare using this nanotechnology. And also wrinkled resistance, I mean mudatalu leni cloths kuda we can fabricate using this nanotechnology. And also strengthable cloths also we can use using nanotechnology. And also UV blocking cloths also we can prepare. Similarly, computing cloths and antibacterial cloths also we can prepare. Nowadays, in the food industry, the packing materials preparing from the nanotechnology. So if you keep your fruits or your vegetables in that packing material, your vegetables may not be damaged up to 30 days, because that packing material are coating with the silver nanoparticles. Silver nanoparticles having the antibacterial activity. So once any bacteria entered into that packing material or interact with that packing material, I mean that silver nanoparticle, it will, the cell wall of that bacteria will be damaged. So ultimately the bacteria will die. So see, okay, coming to the here. So similarly, sensor based cloths also we can prepare, and optical display cloths also prepare using this nanotechnology. So these type of cloths we can, I mean fabrics we can prepare using this nanotechnology. That's why this nanotechnology have a good impact on the textile industry. Coming to the biomedical and healthcare, mainly these three: therapy. Therapy means treatment, curing. Theranostics, I mean diagnostics. So in the disease diagnosis also we can using disease diagnosis also can be do using these nanoparticles. Similarly, imaging also. For example, you can see MRI. In MRI case also, the nanoparticles will sent into the blood, so that nanoparticles are manipulated using the magnetic field. That technique is called MRI. So where there is a disease, that magnetic particle will move there in our body. so will accumulate that position. For example, if you have a brain cancer, if anyone have a brain cancer, so that particles will move into the brain and they will interact with that cancer cells, though those nanoparticles will stay there. Then if you apply the magnetic resonance magnetic field, so that brain part will become a how can I say, it will be resonance, it will show the some resonance. Using that resonance we can that your EC means that how can I say that Fourier transform peaks will come. So using that signal processing technique, so this magnetic nanoparticles are located in the brain. It means that that person have a cancer. So using that type of imaging also can be occurred through these nanomaterials. So these nanomaterials are very important in the therapy. I mean, drug delivery and those things also using. I'm not going in detailed because of lack of much more time. So therapy and diagnostics and imaging, these all parts of the healthcare system. Nanoparticles have, or nanoparticles means nanomaterials have a good involvement. I when we have a free time, so I will explain these all things in detail. Yeah. Okay, next coming to the electronics. Here, so many applications in electronics, but here I have shown only two. So spin crossover materials, because spin crossover materials are very fascinating materials in nano. I will explain you. So just I will take 1 minute for this slide. So generally two types of the spins are there here. For example, here you can see here the maroon color is in this image, here is white. Okay, the material is same, but it shows two colors. When, for example, if you take the low spin materials, low spin means the electronic spin states is here. So in this state, here this is a ground state. I guess in your intermediate you can study the molecular orbital theory. So in that one, this is the HOMO LUMO. So here all the electrons are occupied. So according to Ohm's rule, these electrons are firstly occupied because these are the low energy particles. Okay, coming to the here. So when the low spin state, the material shows this maroon color. When you apply the UV light, so these electrons will move into the LUMO state. I mean, next energy level. So this transformation, the color of the material will be changed. So here white color. So in high spin state of these materials will show different color, and at low spin state it shows different. Here external stimuli is the UV light. So for example, this type of technique you can see here. So these are the display boards. Generally you can see in the railway stations. For example, Vizag railway station, Bhimavaram railway station, you can see this type of clocks. You can see here, you can see when the UV light came, so it become high spin state. If there is a no UV light, it is in a low spin state. That's why when the UV light, so this line, I mean this 30, for example, 1238 will be visible when here the material is in high spin state. When there is a no UV light, so there will be a no brightness in this one. So it seems not dark. So the time will not be visible. That is called low spin state. So this type of spin crossover materials used in this type of display items. Another type of materials are also there, that is spintronic materials that will use in the flash memory devices. For example, here also the same scenario. When the low spin, the material, the data will be stored. When you change into the high spin state, the material will be erased. So using that switching happen using these spin crossover materials. Nowadays, the spin crossover materials usage is very high. Here, in this case, the external stimuli is the magnetic field. Here is the external stimuli is the UV light. So that is the difference. So based on here, the material is different. Here, the material is different. I mean, spin crossover type of material is different. So this spin crossover material can be used in the data storage devices, in the reading and erasing case. In the reading case, low spin, just imagine In the high spin case, erase the data. So such type of spinning will happen. So using this type of materials in electronics to fabricate this type of devices, many applications are there, but here I have shown very few because of time factor. Next, I already told you the stretchable gold. In future, your electronic field is going to be a wearable electronic field. I mean, so the stretchable motherboards will be fabricated soon. So that fabricated motherboards you can wear on your clothes also. Wearable electronics field will be open soon by using of this nanotechnology. I am sure within 1 or 2 decades, these all inventions become a commercialized. So you will see revolutionized electronic field because of this nanotechnology. Yeah, so these things will be in environmental field. So I'm going little fast. This slide I'm skipping because this is not relevant to you. So the renewable energy also, the nano having good mark on the energy storage systems also. And here you can see this is very interesting work. So Juvex company, I mean ZPM's Arvex company have prepared one lightweight boat. So it is very fast boat in the world. So because of this material is nanotube reinforced carbon fiber. I mean, this is a carbon fiber reinforced mechanism was they used. So that type of material have been used to prepare this lightweight boat. So this was manufactured by ZPMS Arnovex company. So the cost of this one is very high, but I didn't find the speed of this one. So the fuel usage also I didn't find the details, but this is the initial innovation in the boating sector. I mean boat manufacturing sector. Now coming to the another interesting application. In 2005, the Mercedes-Benz company released one car that is M-Class version. So in this M-Class version, they used the scratch resistance paint. That paint is prepared by the nanomaterials. So scratch free. Such type of paints were used, but it was not yet commercialized completely. That's why that material has not yet come explored so far, but the research is going on in this sector. In future, we can see those all results. So this is about the applications of the nanotechnology somewhat. So now I will show you my work, a case study as one exam, one application. So I will change the PPT. Just a minute. Sorry, have you seen the second PPT? Sir, anyone please respond.
No,
Hello?
sir. It's not. No, sir.
It's visible? Is it
No,
visible?
No, sir.
No? Just a moment. Now, madam, is it okay now?
yes, sir. Yes, sir.
Okay, thank you. So this is my research work. So I have shown many examples of nanotechnology. So my work is related to the biomedical application. So during my PhD, I have done my work in the biomedical field. In this biomedical field, I have used the nanotechnology to develop the single cell manipulation tools. So my title of the work is Development of Magnetic Tools for Single Cell Manipulation. The term is little new for you. So I will tell you what is the single cell analysis. First, you can understand the single cell analysis. Then I will reveal about my work, what I did and how I explored my work in the single cell analysis. Okay, come to here. So just understand about this slide. So here I have shown one figure here. So just imagine in the population of in the disease population. So generally three types of patients are there. So number one, no disease. Second type is acute stage of disease. Third one is the initial stage of that disease. In the disease population, for example, in the cancer, for example, breast cancer population, if you take the breast cancer disease affected population, so generally you can see three types of the patient. First type of patients are no breast cancer. Someone have acute stage. Acute means severe stage, matured stage of that cancer. Initial stage means very just it is in the early stages of that cancer. So that is the third type of patients. So the first one, just ignore it, because these people's doesn't have any cancer, so just ignore this category. So we have only two categories here. One is the severe stage and initial stage. Okay, here you can see if you go to the laboratory, I mean diagnostic laboratory, so what they will do, they will take a 1 ml or 10 ml of your blood sample. Just they put one syringe into your vein, puncture the vein, they took around 1 ml of the blood to get the analysis. So for that 1 ml of blood, so you will get so many millions of the cells. Okay, before here I will show you okay, later I will tell you that one. Okay, millions of the cells they will collect it. So what that people will do, I mean diagnostic people will do, so that millions of the cells they will analyze, they will give average analysis. Average analysis means, for example, 1 ml of blood having 10 millions of the cells. So the result is the average of that 10 million cells. In across the world, all diagnostic laboratories results are based on average results of all the cells. So what will happen if you do the bulk analysis in these two cases? So see here, for example, acute stage. Acute stage means severe stage. For example, here you can see one number cells are here two types. Here one is one number of copy, because when the disease affect, the changes happen in the body. I mean body means cells, there is some changes will occur. So if you see here how many cells generally in one out of that million, so I have here shown around 1 2 3 4 5 6 7 8 9 10 11 cells I have shown here. Out of this 11 cells, only 5 cells are affected by the cancer. So it means that these 5 cells are cancer cells, rest of the cells are normal cells, because 10 means it will be duplication within a 1 minute, 10 times it will be duplication, because the cell division will be very fast in the cancer cell. So only one cell affected sorry, 5 cells affected in this population of cells in the mature stage. Coming to the initial stage, so only one cell affected, but this have a capability division of 50 cells within a 10 minutes or 1 hour, whatever it may be. But here also 50, the result is 50, here also 50, but here only one cell damaged, but here 5 cells are damaged, because this is the acute stage, more cells are damaged, but here one cell is damaged. If you do the bulk analysis, the result is the same in the acute stage as well as initial stage guy. The result is same, because the average of the cells. So in our in the current scenario, in all the diagnostic laboratories across the world, not in India, in USA, everywhere, highly developed medically sound countries also doing the same scenario, following the same scenario. That is bulk analysis. It is the average of the cell population, total cell population. So this bulk analysis give both are in the acute stage. But if you do the single cell analysis, take the single cell and analyze, okay, this cell no affected, this cell no affected, this cell no affected, so only one cell affected. So if you understand that one, so you will do the therapy very easily. So in the initial stages of the cancer, we will treat with the chemotherapy, but in the acute stage, so we cannot give, I mean the results of that chemotherapy will not be good. But in the initial stages, the therapy of the chemotherapy, the chemotherapy results will be good. But in the acute stage, it will not be good. So if you use the single cell analysis, you can detect the disease in the early stages. So the early diagnosis can be possible using this single cell analysis instead of bulk analysis. So that is the beauty of this single cell analysis. So the single cell analysis gives the accurate results. So in now the USA has giving more funds on this research, single cell analysis, because this is the very innovative diagnostic analysis in the medical field compared to the bulk analysis. So the only problem why this single cell analysis is not commercialized so far compared to the bulk analysis, the reason is here. I will tell you, because the collection of the single cell is very difficult, because the cell size is approximately, for example, small cell size is 1 femtoliter. 1 femto means 10 to the power of minus 15 liter of the solution. If you pick up using the pipettes or something, then you will get this cell. Small cell, the size is 1 femtoliter. Volume it occupies. If you coming to the big cell, 1 picoliter, it is 10 to the power of minus 12, minus 15. So this is smallest volume. Generally, in our laboratories or in advanced laboratories, micro pipettes are there, 10 to the power of minus 6. Volumes can be handled using these pipettes. But the single cell occupies how much volume of the liquid? So 10 to the power of minus 12 big cell, small cell averagely approximately 10 to the power of minus 15. So this is minus 6. So approximately so many zeros after point is there. For coming to the this one, so 6, 4 plus 5 minus 9 difference is there. So this micro pipettes cannot be give answers for this single cell analysis. Isolation of the single cell, it is not possible. So what I have done, this is the research problem in my research. So I have developed a magnetic tools to collect the single cells. I will show you how I collected that single cells using my research. This is my research problem. Collection of the single cell. Okay, this is the state of art. Time is dead. Okay, this is my technique. This technology I have developed for the single cell analysis. So I will tell you about my setup. So you can see in this slide. So these are 4 magnets. I kept the arrangement is like this way: north south, north south, south north, south north. So 2 magnets total. I kept 4 magnets in the circular direction. So 2 magnets in south direction, 2 magnets in north direction. So in this circle, I kept in between 1 perm alloy magnetic structure. So this is the magnetic pattern using lithography technique. So I sputtered on the silicon vapor substrate. Actually, the silicon vapor substrate is this one. So these are the 4 magnets here. This is the microscope. So this is a silicon vapor substrate. So on this silicon vapor substrate, the perm alloy soft magnetic structures, I mean nickel and iron, the composition is 80:20%. So that one pattern on this silicon vapor, then I put it here. Then I kept some of the particles, magnetic nanoparticles, I put on this one. So then I rotate these 4 magnets. So these magnetic particles on these patterns will move based on this circular. You can see here. So I am rotating these 4 magnets in the clockwise direction. The particles kept on this magnetic structures, so it is moving. So it is going forward direction. When I reverse these one into anti-clockwise direction, the particles will move in the backward direction. So here the magnetic particle move forward and backward. So the chip orientation is like this way. This is my microfluidic chip. So this is the microfluidic channel. So this is the silicon vapor. Here I kept $250. So because this reflects my chip size is equals to this quarter size coin. So here this silicon vapor, this magnetic structures are there. So here I kept inlet and outlet. in this inlet I will send the magnetic particles. So that magnetic particles on here, so it will be moved. So then I kept this microfluidic chip in between these 4 magnets. So then you will get a doubt. Sir, you are telling about the cells, but you are telling here magnetic particles. Okay, so what I did, because I am a chemistry guy also. So this is the engineering. Then I introduced the chemistry also. So I attached bacterial cell or cancer cells, normal cells, every cells I attach it to this magnetic cell. Like this way, some conjugation I have used, some chemistry. Okay, I will, yeah, this chemistry I have used. So these are the bacteria. So these are the magnetic particles. Using some chemistry, I have attached these magnetic these bacteria or our cancer cells attached to these nanoparticles. So here the magnetic particle and the bacterial cell or cancer cell, whatever it may be, these chemistries I have used. So that structures, if I keep it here, those will also move. So based on this movement, I will collect the single cells. Okay, I will tell you those things. Okay, before going to that one, I have narrated one scenario. This is my philosophy. In my work, I have generated one philosophy also. So everyone knows, you people are very well know about the Ohm's law. So based on that Ohm's law, I applied here. You can see. So I can, this is a conductor. Just imagine this soft magnetic pattern I imagined as a conductor. This magnetic particle I have imagined as an electron. So this magnetic orientation, this external magnetic in the clockwise direction or anti-clockwise direction, I can consider as a battery. So this is a driving force. That's why this magnetic field. So this is called battery. So it is, if it is these, these 4 magnets in the circular arrangement, if move in the clockwise direction, I can call it as a plus direction. If I rotate this one anti-clockwise direction, I will call it as a minus charge. So when, if the particle, I mean the electron move in the forward on the conductor, so I will put plus charge. Plus charge means clockwise direction. If it come backward, so I will rotate anti-clockwise direction, that will call it as a negative charge. So that type of philosophy I have generated. Then you can see my work, how it would be. So based on that concept, I have developed the circuitry elements for matter. Matter means material, nanoparticles. In your case, so here you can see the conductor. The conductor is here. My case, that magnetic pattern like this way. So here, in your case, the electron will move here. But my case, the particle, magnetic particle move in the forward direction, backward direction. In your case, the external means the electron moving force is battery. Here, my moving force is this magnetic field. See here, so that's why the flow of matter like electrical current forward and backward, I can call it as a matter conductor. In this case, I have designed like this way, similar to diode. In your diode, so what will happen? The electron flow in one direction only. But here also same. If the particle will move in the forward direction, when will back into this one, it will not go this direction, it will go upward direction. So I can control the matter in one direction using this architecture of my pattern. Similarly, capacitor. What will happen in the capacitor? The electric charge will be stored. In this pattern, the matter will be stored here. So that's why this is called as a matter conductor. I have designed this type of philosophy for my PhD work. I'm so proud. I have took 3.5 years to complete this work. And now another circuitry element also I kept a transistor. In transistor, what will have switching mechanism will be there. Here, a current line, I have kept these 2 patterns in these shapes. When the particle is moving here, when the current is passed in this electric line, it will be jump that magnetic particle to here. If there is a no current, it will go in this direction. So I can switch the particle like your electron. Just think about, so this is a conductor copper wire. Here electron is a magnetic particle. So these all results I am going to explain the coming slides. So first focus on the conductor. In your case, conductor. My case, it is a matter conductor. I will show you. Yeah, here you can see I have shown two results: experimental results, theoretical results. Theoretical case, I have used the Maxwell software to locate the where is the high kinetic energy, sorry, high potential, where is the potential energy is high, where is the potential energy low. Where is the potential energy low, the particle will be moved there. Here this blue color indicates the potential energy minima, this red is kinetic energy is maximum. Okay, here you can see, so this is my magnetic chip. So here this red color will moving, so it is, this is actually chip. So the magnetic field is applying like this way, means the four magnets are rotating like this way in this video, just imagine. So that rotation I have represented using this video, sorry, this arrow mark red color. So H is applied in magnetic field. Applied magnetic field is that external magnetic field is coming from the four magnets. See here. So the particle, so I am applying the magnetic rotating field in this direction, clockwise direction. So the particle is moving in the forward direction. This is the real experiments. This is the theoretical simulations. This is the simulation data. This is the experimental data. Next, I reverse this one, anti-clockwise rotation applied external field. Let's see, the particle is moving from backward direction. So I can call it as this is a conductor because the particle is moving forward and backward, like your current moving, electron moving forward and backward by applying the electric current using battery. Here the electric rotating field is the battery. So forward and backward. Here you can see, so this is the only magnetic particle. Here the cell, these are the B cells. B cells means these cells are in our blood. In our blood means here I have took rat cells, rat spleen cells. So you will see the, so this is the cell moving on the pattern. So this is the pattern. So see, this is forward direction. I applied the magnetic field in the rotating. The magnetic nanoparticles are attached to the cells. The magnetic particle size is 50 nanometer. So those nanoparticles are not visible, because of that microscope cannot be captured that nanoparticles, because the size of the particle is around, not particle, sorry, the size of this cell is 3 micrometer. That's why this is visible in this microscope. The nanoparticle size is 50 nanometer. So it was not visible in this microscope. So forward and backward. This is a cell. This is not particle. Here I have used big particle. Here I have used small particle because of this movement case. Here also you can see. So this is this dark one is the particle. This green color one is the bacteria. Green color bacteria. So you can see also. See, this is moving forward direction when I apply the clockwise direction field. Now I will reverse it, so it will come out. You can see. So this blue color, yeah, reverse it. Reverse the rotation field anti-clockwise direction. So the magnetic particle moving come backward direction. So similarly, I have done some more interesting videos. So these cells I have stained with some good colors. Then I have took the fluorescence image of these cells by applying the stain treatment, I mean the coloring agent dye treatment. So clockwise direction, the cell is moving on this one, because this is the fluorescence a video. That's why there is no visibility. Actually, here is the pattern is there, but in the fluorescence spectroscopy, only the wavelength which can be target only this dye. So this is about the matter conductor. Next I will show the matter diode. Here you can see this guy is moving forward. Okay, now I reverse it. Okay, here the reverse video is here. So here I can control the direction. So here only forward direction. Here you can see, here horizontal pattern is there, vertical pattern is there. Once the particle reaches here, so I applied the reverse magnetic field. Let's see here. So reverse magnetic field, this particle doesn't move to this side, doesn't follow the horizontal particle, horizontal pattern. It follows the vertical pattern direction. So based on this architecture, I mean based on this structure, this design, we can control the matter directionally. I want to emphasize that one in this result. So now coming to the matter capacitor, here you can see clearly this is the magnetic particle, this is the bacteria. So this is a cell I have attached using some EDC NHS coupling chemistry. And the first guy prepared such type of structures during my laboratory across the world also, I can say proudly. Yeah, here you can see the particle is moving and cell also moving along with. So this is, I can say it is as the trapping agent, trapping pattern, like charge storage here in the normal capacitor. In here, this is a matter capacitor. This square pattern, the particle or the particle attached cell cannot be come out. So these type of tools I have developed. So once this particle come here, so I will collect this liquid directly, then I will get a single particle or single cell from this one. So after getting this combination, then I change the pH, the cell will detach from this magnetic particle, then I will collect a single cell very easily. So here this is the bacteria, this is the B cell, this is the animal cell. Here you can see, this is the particle case also. Here I have shown the some cell result. Here you can see the particle results. So this is the capacitor, matter capacitor. Once enter into this design, so the particle cannot be come out, even though it is the clockwise direction or anti-clockwise direction field. So now it is clockwise. Now I reversed the rotation field in this direction. So it will be not come out this side. It will be trapped in this square pattern. So similarly, this is a bacterial cell, this is a animal cell, this is a cancer cell. I will tell you the cancer cell result also. The cancer cell is big compared to the animal cells. This is human cell, human breast cancer cell, this one. We collected from some cancer hospital in Korea. So see, this is the cancer cell. The back side, have you seen two particles? Those are the magnetic particles. So once enter into this square pattern, it will not be come out. Like in your electronics, the charge storage in the capacitor. Similarly here, the matter has storage at one position, localized at one position. Next, I'm going to show you the matter transistor. So here you can see just a minute. Here you can see. So these three guys are moving. This is the one electric line. There is a no current. When here the current is on, yeah, again I'm saying three guys are following here. Three guys are following here on this pattern. So the first guy case, we didn't current on. So this guy will move vertical pattern, follow the vertical pattern. When this guy approaches here, when I switch on the current using this current line, so this will jump to this slide, horizontal pattern. So you can see the result. So no current on. Now the current on, so this guy jumps to this side. Now the current off, this guy is following the vertical pattern. So using this system, we have developed the matter transistor, means switching the matter. So here you can see the cell result. Yeah, cell is transparent. That's why the visibility is little difficult. So here you can see, okay, current on, so it will become this one. If there is a no current, it will follow like this way. So first one is no current on, so it following the vertical pattern. When this guy came here, then current on, so this guy changed the direction. So that's why this is called matter transistor. Next, this is our heart, my work. So this work I have published in Nature Communication Microfluidics, US patent, Korean patent, granted also Now in the technology transfer case through Samsung. Okay, this is my final work. These two videos will show my entire work. So how much novelty is there? So far I have shown you the matter conductor, matter transistor, matter diode, matter capacitor. Now these all circuitry, matter circuitry elements I assembled in a one system. See here. So here you can see before going to this one. So here I will show you in this video two parts are there. First the animation will come. Next the real experimental will come in this video. Here I will show the cell collection. Okay, here you can see. So these yellow lines are the current lines. These are the magnetic patterns. So here you can see the diodes using at this T junctions, and this is a capacitors. These current lines will act as a transistor system. So here you can see first using this structure, I can locate my particles anywhere. I can play with my particles also. You can see. So for example, in this case, I want to locate my particle in this room, in this room, in this room, in this room, in this room. For demonstration, I have selected this room. Okay, you can see. Yeah, first I want to kept particle here. Next, I want to kept in this room my particle. Just by switch on, switch off, that scenario, we can manipulate the particles at a desired location as per my convenience. So this is the animation. Now let's see this is the real experiment. So the whatever the designated things, the particle will move. So here no current on, so the particle is moving up. Here also no current, so the particle is moving up again. So now the current on here, so the particle will come to this line. So my particle I trapped here. Next particle I want to trap here. So based on one, I switch off. Here I switch on this one current, then the second particle will come into this room. Yeah. Next I have shown these two also. These two and these two, this one. Yeah. Here one more particle, another particle is coming. So that one I want to trap in this room. Yeah, see this room. Yeah, switch on, then it came to here. Next I want to keep it here. So no current on, but once it reaches I current on, so then it won. So I can play with the beads. Beads means nanoparticles or something. So once I attach the cells, so I can kept these particles in this location. So then I will easily collect that single particles using these circuitry elements. So this is about the magnetic particle result. Here you can see the cells attached. Here also I used the cancer cells. See that cancer cell. So in this one, I guess in these three rooms, let's see. So this is a cancer cell is coming. So then current on. So it will be trapped here. Another cell is coming in this pattern. So it will trap here. Another cell will come here. So it will be trapped here. So this is the cancer cell. That backside there is a dark spot, that is a magnetic particle. So I can play with the magnetic particles and I can designate my cells. Cells means I can operate the cells at a desired location. Then I will collect simply this single cell by using this technology. So and also I have done one interesting experiment. So converging of the particles and deconverging of the particles. Let's see, this one also published in the Asian materials. Here I kept some sensors. See, this is the, I can say this this design I have prepared from the inspiration of spider web. I know the spider web. I have seen the spider web design. So based on that inspiration, I have prepared the spider web design patterns. So let's see the particles I have kept at these locations. All the particles have gathered single place. You can see. Yeah, I kept the particles here. So all the particles are coming here. I applied the anti-clockwise direction. So all the particles are delocalizing at one location. See the density of the particles. When I kept here sensor, so it will give signal also. Then I reverse the field, all the particles is come out. So I did one interesting video. So I labeled with some dye, coloring agent, coloring material I have coated to these magnetic particles. Then the video will become very attractive. You can see here. Yeah, the color particles are locating here. This location is this one actually. So this is optical microscope. Only the fluorescence particles will be highlighted. The remaining will be blank. So now converging anti-clockwise direction. When I reverse, okay, wait, I will reverse this field. Then, okay, now I am applying the anti-clockwise. Now I reverse it. Then all the particles will go away from that place. So this type of interesting tools I have developed during my PhD. So those results I was published in high impact factor journals. So the Nature publishing, this is more than 10 impact factor, and Nature Science, Nature Communication, Nature Group. So this work also published in high impact. The impact factor is around 17 or something like that. So, and also I published 2 patents. I mean, granted also US patent, international patent. So I'm very happy about my PhD work. Thank you so much for giving me this opportunity to explore my work at this platform. Madam, sorry to take 20 minutes extra. Now the time for questions. If you have any questions, if the organizers allow, I'm ready to answer those questions.